Welcome back to QHSE Talks. I want you to imagine, just for a second, an industrial factory floor in, like, the early 1900s.
Oh, that is usually a pretty bleak picture.
Right. It really is. You have a worker operating this massive, steam-powered mechanical press.
With zero machine guards, I'm guessing.
None at all. And the lighting is terrible, and this person has been on shift for, 14 hours straight.
Which was just completely standard operating procedure back then.
Yeah, exactly. So when that worker inevitably loses an arm to the crushing weight of that press, the company's response historically was, well, it was really simple. They blamed the worker.
Yeah, they called it carelessness.
Exactly. They called it an unsafe act. And that mentality, that dominated industrial operations for decades.
It was essentially the default setting for corporate liability.
Right. But today, if that same incident happens, the modern safety framework doesn't look at the worker first. It looks at the machine.
Yes. It asks, why was that hazard even allowed to exist in a way that a human being could interact with it?
And that fundamental shift in philosophy, that is exactly what we are unpacking today. So whether you are cramming right now for the Associate Safety Professional exam, the ASP, and feeling the pressure of that ticking clock.
Which is very stressful, I know.
Oh, totally.
Yeah.
Or maybe you're just a seasoned practitioner looking to, sharpen your real-world risk management skills. This QHSE Talks is custom built for you.
That historical context is really the perfect place to start, I think, because we are tackling a foundational element of the entire profession today.
We really are. We are focusing on ASP Domain 2, Topic 2.
Right, which requires candidates to apply the hierarchy of hazard controls. And, this isn't just some abstract theory.
No, not at all.
This is the actual mechanism by which that historical shift from blaming the human to fixing the environment is implemented in the field.
And if we actually look at the official ASP exam blueprints, Domain 2, which covers safety programs and concepts, that makes up a massive 25% of the entire exam.
Yeah, a full quarter of your overall score.
It's huge.
Yeah.
1/4 of your score relies on understanding this framework. So you cannot pass the exam, and frankly, you cannot effectively protect workers in the field without having the hierarchy of controls just encoded into your operational DNA.
It has to be second nature.
Exactly. So to make sure we are giving you the most accurate, battle-tested information today, we pulled together a really significant stack of source material.
Oh, we went all in on the sources for this one.
We did. We are looking directly at the ASP and CSP exam blueprints. We're cross-referencing the ISO 45001 standards for occupational health and safety management systems.
And the ANSI Z10 guidelines, which are crucial.
Right. Plus, we're integrating comprehensive study guides and a really massive treasure trove of actual Bowen EHS practice questions, just to see how these concepts are actually tested.
Because the mission for our discussion today, it goes way beyond just, reciting a list of terms for you to memorize.
Yeah, memorization won't save you here.
No, it really won't. Rote memorization might get you a few easy points on a multiple choice test, but it will completely fail you when the exam throws a complex, multi-layered scenario at you.
Which they absolutely will do.
Oh, guaranteed. The goal of this QHSE Talks is to deeply understand the underlying philosophy of risk management.
Right. We want you to understand the structural vulnerabilities of human psychology, the mechanics of industrial design, and that cost-benefit analysis required to make those split-second defensible decisions.
Exactly. But before we even look at the specific tiers of the hierarchy itself, we really have to establish the prerequisite.
The foundation.
Yeah, because it is a fundamental law of safety management. You cannot control a risk that you haven't identified.
That makes perfect sense. The hierarchy of controls doesn't just exist in a vacuum.
No, it's the output of a much larger engine. And the source material outlines an 11-step hazard and risk assessment process that basically serves as that engine.
And I want to spend some time exploring how this assessment actually functions, because the exam is going to test your ability to sequence these steps correctly.
The sequencing is absolutely critical. So the very first step of that 11-step process is establishing manageable parameters.
Right. And this is where I feel like a lot of novice safety professionals fail before they even start.
Oh, all the time. Because if your directive for management is simply to, assess the safety of the entire manufacturing plant.
The scope is just way too broad.
Exactly. You will be completely overwhelmed by data, and you'll end up missing the micro interactions that actually get people hurt.
So establishing manageable parameters basically means putting a strict strict fence around a specific activity.
Yes. You define whether you are analyzing daily routine operation, or if you are looking at a maintenance shutdown, or maybe a system startup.
Because the hazards present during a routine operation are completely different from the hazards when a machine is being torn down for repair.
Exactly. You are essentially isolating the variables.
Okay, so once you have that specific scope locked in, what is step 2?
Step 2 is identifying the potential hazards. This is where you catalog the physical realities.
Like the chemicals being used.
Right, the chemicals, the kinetic energy of the machinery, the thermal energy of a furnace, maybe the biological hazards if you're in a lab.
You're just looking at the raw potential for harm.
Exactly. And that leads us directly into step 3, which requires considering the failure modes.
Failure modes. And
Yeah.
it's such a crucial concept because we aren't just looking at how the machine operates when everything is perfectly fine, right?
No, we have to look at what happens when the system breaks down.
Right.
A failure mode analysis asks, well, what happens if the primary cooling pump fails? Does the reactor vessel overpressurize?
Or like, what happens if the facility loses power while a worker is suspended up in a man basket?
Yes, exactly. What happens if a critical valve gets stuck in the open position? Identifying the hazard is knowing the chemical is toxic. Considering the failure mode is understanding exactly how that toxic chemical might escape its containment.
That distinction is so important. Which brings us to steps 4, 5, and 6, which seem to be the data gathering phase.
Yeah, step 4 is evaluating the frequency and duration of exposure.
So this is basically a simple metric of time.
Right. Is the worker interacting with this hazard for 5 minutes once a month? Or are they standing right next to it for 8 hours a day, 5 days a week?
And that time factor is going to heavily influence the next 2 steps, right? Assessing the potential severity of harm and determining the probability of that occurrence.
Exactly. Severity and probability are the 2 primary axes of literally any risk matrix you will ever use in your career.
Let's break those down. Severity asks about the worst case consequence, right?
Right. Are we looking at a minor laceration that just needs a bandage, or are we looking at a catastrophic explosion with multiple fatalities?
And then probability asks how likely that consequence is to materialize.
Yes, factoring in the frequency of exposure that we just established back in step 4.
Right. And when you plot severity against probability, you get a clear picture of the threat. And that's step 7, defining the risks.
But identifying a risk doesn't actually solve the problem.
No, because in any industrial setting, you're going to identify dozens, if not hundreds of risks.
Which is exactly why step 8 is so vital. Step 8 is ranking those risks in priority order. It is an exercise in industrial triage.
Triage is the perfect word for it, because a safety professional has limited resources, a limited budget, and limited time.
Yeah, you can't fix everything at once. If you spend all your capital trying to engineer away a risk that has a really low probability and low severity, like, I don't know, a paper cut in the administrative office.
Right, while ignoring a high severity, high probability risk out on the production floor.
Exactly. You are failing at your core objective. You must rank the risks to dictate where you deploy your resources first.
And that prioritization leads us to step 9, developing remediation proposals.
Yes, and this is the exact moment the hierarchy of hazard controls becomes relevant.
Because you've scoped the problem. You've identified the hazards and failure modes, calculated the severity and probability, ranked the risks, and now you actually have to propose a solution.
Right. The hierarchy is the universally accepted framework for figuring out exactly how to fix the risks that you just prioritized.
So as we transition into discussing those specific remediation tiers, we have to return to that historical shift you mentioned at the start of this QHSE talks.
Yeah, that old blame the worker mentality. It was incredibly convenient for corporations.
Oh, extremely. Because if an injury is entirely the fault of a worker's carelessness, the company doesn't have to spend a dime re-engineering the production line.
Exactly. But the modern safety philosophy, the philosophy that the ASP exam rigorously enforces, operates on a completely different premise.
Right.
The basic premise of the hierarchy of controls, which is highlighted explicitly in the Bowen EHS practice questions, by the way, is to eliminate the hazard before it becomes a risk.
I want to use an analogy here to just ground this abstract philosophy into something incredibly tangible for everyone listening.
I love a good analogy. Go for it.
Okay, think about your own home. Imagine you have a massive, gaping hole in your roof, and it is pouring rain outside. The rain is pouring directly into your living room, creating this huge, slippery puddle on the floor.
Okay, a terrible situation.
Now, if we apply that old blame the worker mentality to this situation, you would simply buy your family waterproof jackets hand them some slip-resistant shoes, and tell them to walk very carefully around the puddles.
Wow. And if someone slips and falls, well, you just blame them for not being careful enough.
Exactly. It sounds completely absurd when you frame it that way, but that is exactly how so many legacy safety programs operated.
They focus entirely on managing the human behavior around the puddle rather than addressing the actual water falling from the ceiling.
Exactly. The modern hierarchy of controls forces a different approach. It demands that you don't start by buying jackets. You start by trying to fix the hole in the roof.
Because the rain is the hazard and the puddle on the floor is the risk.
Right. And the jackets, well, those are your personal protective equipment. The safety industry's central tension, the constant battle every professional fights daily, is that buying jackets is always going to be faster, cheaper, and easier in the short term.
Oh, without a doubt. Compared to hiring a crew, shutting down the house, and rebuilding the roof, buying jackets is easy.
But the jacket approach is structurally fragile. It relies entirely on every single family member remembering to wear the jacket and walking perfectly every single time.
Which is impossible. Humans make mistakes.
Exactly. The hierarchy forces us to look at the roof first, because fixing the roof protects everyone, regardless of their behavior.
And that tension, between the short-term cost of a quick fix and the long-term reliability of a structural fix, that is the defining narrative of the hierarchy of controls.
So when we look at the top tier of that hierarchy, the methods aimed at fixing the roof, we are looking at the absolute gold standard of risk management.
Let's break down that top tier. We are talking about avoidance, elimination, and substitution.
These are the most effective interventions possible. But the source material highlights some very specific, nuanced differences in how the major standards actually define them.
Yeah, understanding the difference between the ISO 45001 standard and the ANSI Z10 standard on this specific point, that is prime exam territory.
It really is. It's a subtle but critical distinction. ISO 45001, which is the international standard, lists elimination at the very top of its hierarchy, followed immediately by substitution.
Right. However, the American National Standard, ANSI Z10, introduces a step before elimination. ANSI Z10 explicitly adds avoidance as the absolute highest level of control.
Let's clearly separate avoidance from elimination, because I think they sound pretty synonymous to a layperson.
They do, yeah.
If avoidance sits above elimination in the ANSI standard, it has to involve a distinct mechanical difference in how we approach the hazard. Elimination means taking a hazard that already exists in your process and physically removing it.
Right. Avoidance, on the other hand, implies dodging the hazard before it is ever introduced into the ecosystem in the first place.
That is the precise distinction. Avoidance means altering the fundamental business plan, the facility location, or the core design to ensure the hazard never even crosses your threshold.
Think of it from a project management perspective. If a corporation is planning to build a new chemical processing facility, and the initial blueprints place that facility in a known high-risk floodplain,
Avoidance would be the decision to just purchase a different plot of land on higher ground.
Exactly. You aren't building a seawall to manage the floodwaters. You are changing the plan entirely so the flood hazard never even interacts with your workers. Avoidance is the ultimate proactive measure.
It is making the hazard a non-issue before ground is even broken. Elimination, then, is applied when the process or the hazard already exists, and we make the engineering or operational decision to completely remove it.
Let's look at a specific scenario pulled directly from the Bowen EHS practice problems to illustrate how this is tested on the exam.
Okay.
The scenario involves a hot works operation, specifically brazing.
Now, brazing requires an open flame and generates extremely high heat to join metals together, right?
Yes. And in this scenario, the brazing operation is currently taking place inside a combustible dust environment.
Okay, for anyone unfamiliar with industrial hazards, a combustible dust environment is one of the most volatile and catastrophic situations a facility can manage.
Oh, it's a nightmare scenario. We are talking about fine particulate matter, whether it's wood dust, sugar dust, metal dust suspended in the air.
Right, and when that dust reaches a specific concentration, it is essentially an explosive aerosol just waiting for an ignition source.
It is the classic fire triangle or dust pentagon in action. You have fuel in the form of the dust, you have oxygen in the air, and you have dispersion and confinement. All it needs is heat.
So the practice question asks, if a safety professional decides to physically move that hot works brazing operation out of the combustible dust area and into a completely different, safer, non-ignitable environment, what kind of control has been applied?
And the correct answer is elimination. But it is crucial to understand why it is elimination.
Because you haven't actually changed the brazing process itself, right?
Exactly. The worker is still using an open flame. The hazard of the open flame still exists. However, by moving the operation, you have physically removed the ignition hazard from the fuel source.
The specific risk of a catastrophic dust explosion has been entirely eliminated from that specific task.
Yes, you dismantled the necessary conditions for the disaster.
That is incredibly effective. But, what happens when you cannot completely remove the hazard?
Then we move to the next step down in the top tier, substitution. We are still operating at the highest levels of effectiveness, but instead of removing a hazard entirely, we are trading it for a lesser one.
We are altering the chemical or physical makeup of the process.
Yeah, substitution is incredibly common in industrial hygiene. A prime example from the exam study guides deals with industrial solvents used for cleaning machinery. Imagine a facility using a cleaner that contains methylene chloride. Methylene chloride is highly toxic. It poses severe acute and chronic health risks, including central nervous system depression and potential carcinogenicity.
It's nasty stuff. So if the safety professional implements a change to replace that methylene chloride-based cleaner with one that uses ethanol, they have performed a substitution.
Exactly. Let's analyze the mechanics of that trade. Ethanol is still a hazardous chemical.
Right. It is highly flammable.
Yes, but compared to the severe toxicity of methylene chloride, it is a significantly lower risk substance to handle.
So you haven't achieved zero risk because you still have to manage the flammability of the ethanol, but you have fundamentally downgraded the severity of the potential harm.
Exactly. Another classic example you'll see is substituting toxic solvent-based industrial paints with water-based alternatives.
Right. What is paramount here, and what the exam expects candidates to really grasp, is the underlying psychology of why avoidance, elimination, and substitution occupy the absolute top tier.
It fundamentally comes down to the removal of the human variable.
This is the crux of the entire philosophy. These methods do not rely on a human being making the correct choice in a high-pressure environment.
Right. They do not rely on memory, they don't rely on training compliance, and they don't rely on a supervisor enforcing the rules.
Once you completely remove a highly toxic chemical from the facility, the risk of a worker being poisoned by that chemical drops to absolute zero.
The physical environment has been rendered inherently safe regarding that specific hazard. It doesn't matter if the operator on the floor is exhausted from working a double shift.
It doesn't matter if they are distracted by personal issues or if management is pushing them to rush production to meet a quarterly quota.
Exactly. The hazard simply isn't there to exploit those human vulnerabilities.
It's the most robust defense possible. But as a safety professional operating in the real world, you have to acknowledge physical reality.
Yeah, we live in a world that requires cutting steel, melted metals, moving massive weights, and utilizing hazardous energy.
You cannot eliminate or substitute every single hazard. This is just not possible.
So when you hit the limit of the top tier, when you absolutely must use a dangerous piece of equipment or a hazardous process, you have to move down the hierarchy.
If you can't remove the hazard, you have to build a wall between the hazard and the worker. And that brings us to the realm of physical barriers, engineering controls.
Engineering controls represent a really significant shift in strategy. You are acknowledging that the hazard must remain in the workplace, but you are actively altering the design of the equipment, the facility, or the process to physically isolate the people from the danger.
The operative concept here is isolation.
Right. Let's clearly define what isolation looks like by pulling another specific scenario directly from the study materials.
Let's do it.
Imagine a heavy manufacturing environment. You have a 100,000-pound drop forge used to hammer hot metal into shape.
The kinetic energy there is massive.
And the acoustic energy generated by this process is severe. The forge is emitting continuous noise levels of 120 decibels.
Wow. Just to put 120 decibels into perspective, that is the universally recognized threshold of pain for human hearing.
It is the equivalent of standing near a jet engine during takeoff. Prolonged exposure, or honestly even short-term exposure without protection, will cause immediate and irreversible sensorineural hearing loss.
Right. So an exam question will present this 120 decibel forge and ask you to identify the best method of protection.
And a candidate relying on common sense, rather than the strict hierarchy of controls, will reflexively choose the answer that says, provide the worker with high-rated, custom-molded earplugs.
Which seems logical, right? The noise is hurting their ears, so plug their ears.
But within the strict framework of the hierarchy, that is the wrong answer. Earplugs are personal protective equipment. They are the bottom of the barrel.
The actual best protection in the engineering control is to physically enclose the entire forge area with heavily engineered, sound-dampening acoustic material.
Exactly. While the operator controls the machine from a console located entirely outside the enclosure.
Let's look at the mechanics of why that is superior. By building the acoustic enclosure, you have isolated the sound waves. You haven't stopped the forge from making noise, right?
No, it's still deafening inside the box.
But you have prevented that acoustic energy from ever reaching the worker's eardrums. If the worker forgets their earplugs, or if the earplugs don't fit perfectly, it doesn't matter. The engineering control is managing the risk completely independent of the worker's actions.
Another classic engineering control heavily featured in the exam prep is ventilation, but it is vital to distinguish between general building ventilation and local exhaust ventilation.
Oh, that's a good point. General ventilation just mixes clean air with contaminated air to dilute it, right?
Exactly. It just dilutes the room air. Local exhaust ventilation is an engineering control because it mechanically captures the hazardous vapor, dust, or fume at the exact point of generation.
And it physically draws it away from the worker's breathing zone before they can inhale it.
You are manipulating the airflow to create a physical barrier of clean air.
Machine guarding is another massive component of this gear. A saw blade has to be sharp, and it has to spin at high speeds to cut wood. You cannot eliminate the sharp spinning blade.
But you can install fixed guards, adjustable guards, or interlocked guards over the blade.
Interlocked guards are a perfect example of a sophisticated engineering control. Can you explain how those work?
An interlock is a mechanism where the physical guard is electronically tied into the machine's power circuit. If a worker attempts to open the guard door to reach into the dangerous pinch point or cutting zone,
the interlock immediately severs the power.
Yes, bringing the machine to a dead stop before the human hand can even reach the hazard. The barrier isn't just a piece of plastic. It is a designed mechanical response to human interaction.
Now, I have to introduce the reality of the business world here, because the theory sounds flawless.
Always a catch.
Right. If engineering controls are so incredibly effective, if an interlocked guard or a custom acoustic enclosure puts an absolute physical wall between the worker and the danger, why don't companies simply engineer every single hazard away?
Is it purely a reluctance to spend capital? Or are there actual legitimate limits to what we can engineer?
That tension between ideal safety engineering and operational reality is the core of a safety professional's daily life. And the exam expects candidates to know how to navigate it objectively.
Because it is not always just corporate greed. The ANSI Z10 standard provides a very specific framework for evaluating this, referred to as the feasible application factors.
The safety professional cannot just demand a multi-million-dollar enclosure for every loud machine. They have to justify it using these factors. Let's break down those feasible application factors because they really provide the vocabulary needed to argue for safety budgets.
The first factor ANSI lists is the nature and extent of the risk being controlled. You have to ensure the solution is proportionate to the threat.
Exactly. If the risk assessment determined that a specific packaging machine presents a hazard of a minor pinch, like something that might cause a small bruise, but has zero probability of causing an amputation or bone fracture.
Demanding a $500,000 robotic automation system to eliminate that pinch point is not a feasible application of resources. The engineering control must match the severity of the risks.
The second factor is the degree of risk reduction desired. If you are going to invest heavily in an engineering control, you have to analyze whether the proposed design will actually solve the problem or if it will only yield a marginal improvement.
Right. If an exhaust system only captures 20% of a highly toxic fume, it might not be a feasible engineering control because it leaves the residual risk unacceptably high.
The third factor is a major constraint in heavy industry: available technology.
Sometimes the theoretical engineering solution simply does not exist yet. Or maybe it hasn't been adapted to withstand the harsh conditions of a specific industrial environment.
Right, like you might conceptualize a brilliant laser sensor guard, but if the facility operates in an environment with heavy steam and vibration,
the available technology might fail continuously, rendering it completely unfeasible.
You also have to consider recognized best practices in the industry, which is the fourth factor. Like, what are your peers doing?
If every other facility in your sector has successfully implemented a specific type of machine guard, your argument that it isn't feasible loses a lot of credibility.
And finally, we have to address the financial reality.
Yeah.
Cost effectiveness. The exam blueprints emphasize that a safety professional must possess the business acumen to estimate the economic impact of safety issues and solutions.
It is a difficult truth, but it's an essential one. If the cost of designing, fabricating, and installing an engineering control is so astronomically high that it bankrupts the company and forces the facility to close, it is not a feasible solution.
The safety professional has to balance the mandate to protect life with the economic viability of the operation. They have to find the most effective engineering solution within the realm of the possible.
But this brings us to a really critical threshold. Let's say you have navigated the feasibility factors. You have eliminated what you can. You have spent the capital to install the best available engineering controls.
But the forge is still somewhat loud.
Or the chemical vat still emits a trace amount of vapor when the interlocked door is opened.
Or perhaps the machine requires routine maintenance, which means a mechanic has to intentionally bypass the engineering guards to fix the internal gears.
Exactly. When the physical barriers cannot eliminate the exposure entirely, or when those barriers have to be temporarily removed, what is the next step?
We have to cross a major dividing line in the hierarchy. We move from controlling the physical environment to attempting to control the human being.
We enter the realm of administrative controls.
This is a profound shift in risk management strategy. When we utilize administrative controls, we're no longer altering the physical hazard, and we are no longer putting up a physical wall.
We are trying to change the way people work. We are relying entirely on policies, written procedures, scheduling adjustments, and training programs to keep workers safe.
The human element. The exam frequently tests your ability to distinguish administrative controls from engineering controls because they can sometimes look similar on the surface.
Let's look at a classic trap from the Bowen EHS practice questions.
Okay, lay it on me.
The scenario involves a heavy length of metal piping. The question asks, using 2 people to lift a pipe weighing 80 pounds is an example of what type of control?
Oh, I know where this goes. Many candidates will overthink this and assume it is an engineering control.
Yes, their logic is that by adding a second person, you have altered the physical dynamics of the lift, distributing the kinetic load.
But you have to trace the logic back to the hazard itself. The pipe still weighs 80 pounds. The gravitational hazard has not been altered in any way.
You haven't introduced a mechanical hoist, a crane, or a vacuum lift. Those would be engineering controls.
You have simply implemented a management procedure that dictates a behavioral rule. When an object exceeds 50 pounds, require a second worker.
And that rule relies entirely on human compliance, making it purely an administrative control.
Let's dissect another major program that often confuses people. Lockout-tagout, commonly referred to as OLOTO. The goal of OTO is to control hazardous energy before performing maintenance.
When you look at OLOTO in the field, it feels very physical. You are taking a heavy steel padlock and physically locking a circuit breaker in the off position.
So because it involves a physical lock, people naturally assume it must be an engineering control. Why is it universally classified as an administrative control?
It is classified administratively because the physical padlock is merely a tool used to execute a written behavioral program. To understand why it fails and why it sits lower on the hierarchy, we really have to look at the sequential steps of a LOTO procedure.
Walk me through it.
A worker must recognize the need for maintenance, formally shut down the machine, identify all energy isolation points, physically apply the locks and tags, and most importantly, attempt to turn the machine on to verify a zero energy state.
Right. Every single one of those steps requires active human cognition and compliance. If a worker is rushing because the production line is down and costing the company thousands of dollars a minute, they might skip that verification step.
They might apply the lock to the wrong breaker entirely.
And the hazard, the electrical energy, is still fully present in the main line. The lock didn't engineer the electricity away. The written program just attempted to manage the worker's interaction with the switch.
If the human deviates from the procedure, the control fails instantly.
Scheduling is another major administrative tool. Imagine a foundry during the summer where the ambient heat combined with the furnaces creates a severe heat stress hazard.
You cannot air condition a massive foundry. It's just not feasible.
Right. So you implement an administrative control by altering the work schedule. You mandate that workers can only spend 2 hours on the foundry floor before rotating into a cooled break room for 1 hour.
You aren't lowering the temperature of the hazard. You are administratively managing the duration of the human's exposure to it.
Hazard communication programs has fall into this category as well, right?
Absolutely. Spending days training your workforce on how to properly read safety data sheets, how to interpret chemical warning labels, and how to understand the specific health risks of the solvents they use.
It is vital information, obviously, but training does not remove the toxic solvent from the room.
Exactly. If we synthesize this, we have to clearly articulate why administrative controls sit significantly lower on the hierarchy of effectiveness than engineering controls. It comes down to the concept of degradation.
An engineering control, like a physical guard, operates at 100% effectiveness until it mechanically breaks. An administrative control degrades the moment human beings get involved.
Administrative controls are inherently vulnerable to the normalization of deviance. They require constant, unwavering enforcement by management, perfect comprehension by the worker, and a workplace culture that prioritizes safety over speed.
If a supervisor looks the other way when a worker does a single-person lift of that 80-pound pipe just to save time, the administrative control vanishes into thin air.
They do not remove the hazard, they merely attempt to manage the unpredictable variable of human behavior around the hazard.
I think the best way to visualize this difference is to imagine a sheer cliff face near a walking path.
Okay, I can picture that.
An engineering control is building an 8-foot-tall steel-reinforced fence along the edge of the cliff. An administrative control is planting a sign that reads, "Danger, steep cliff. Please walk 10 feet away from the edge."
That is a stark and completely accurate visualization.
Because the sign only works if the person speaks the language, reads the sign, understands the gravity of the fall, and actively cares enough to adjust their path. The steel fence works regardless of whether the person is paying attention or not.
And if the policies, the warning signs, the want-up procedures, and the rigorous training still leave a residual risk.
If the nature of the job demands that the worker must occasionally step past that warning sign and operate right on the edge of the cliff,
We reach the final, unequivocally most vulnerable line of defense.
the last resort, personal protective equipment, PPE.
This is the absolute bottom tier of the hierarchy of controls. We are talking about guarding the human body itself. Safety glasses governed by rigorous ANSI standards, fall arrest harnesses, respirators, hard hats, chemical-resistant gloves, steel-toed boots.
The exam is going to drill deeply into this tier, not just to ensure you know what PPE is, but to guarantee you understand exactly why it is designated as the last resort.
You have to be able to articulate the structural flaws of relying on wearable gear. Let's detail the specific reasons provided in the source material for why PPE is the least effective control.
The primary reason is the most fundamental. PPE does absolutely nothing to eliminate, substitute, or isolate the hazard itself.
The hazard is fully present and fully active. If a worker is on a scaffold and accidentally kicks a 10-pound steel wrench off the ledge, the gravitational hazard of that falling object is fully realized.
Right. The hard hat worn by the worker below does not stop the wrench from falling. It merely attempts to absorb and deflect the kinetic energy milliseconds before it fractures their skull.
If the plastic shell of the hard hat fails, or if the internal suspension webbing is worn out, the worker absorbs the full force of the impact. The hazard completes its attack. The PPE just tries to blunt the damage.
Furthermore, we really have to consider the physical reality of the workforce. Frontline workers are not crash test dummies built to standard specifications.
No, they come in an infinite variety of shapes, sizes, and facial structures. Fit and comfort are massive points of failure for PPE.
A perfect example is respiratory protection. If a facility mandates a tight-fitting, half-mask respirator to protect against a silica dust hazard, that mask must form an absolute airtight seal against the worker's skin.
Right, and if the worker has facial hair, if they have deep facial scarring, or if the mask is simply the wrong size, the seal is broken.
The contaminated air will take the path of least resistance and bypass the filters entirely. The worker is inhaling the silica dust, but because they are wearing a mask, they have a false sense of security.
They believe they are protected when they are completely exposed.
There is also the maintenance and degradation factor. An acoustic enclosure around a machine might last for 20 years. A pair of safety glasses can be scratched and rendered useless in a week.
Respirator cartridges must be meticulously tracked and swapped out based on complex calculation schedules. Fall arrest harnesses must be painstakingly inspected for microscopic fraying before every single use.
The logistical burden of maintaining PPE is immense, and any failure in that maintenance chain results in a loss of protection.
And perhaps the most complex issue, which is frequently tested on the exam, is the fact that implementing PPE can actually introduce entirely new hazards into the work environment.
Let's explore that paradox. How does safety gear create danger?
It alters the worker's interaction with the physical world. Think about requiring a worker to wear a full-face respirator combined with heavy, splash-resistant chemical goggles.
You have drastically reduced their peripheral vision.
Exactly. By protecting their eyes and lungs from a chemical splash, you have inadvertently made them far more likely to trip over an unseen obstacle on the floor or fail to notice a forklift backing up towards them.
Or consider the physiological impact. If you put a worker in an impermeable, fully encapsulated chemical suit to protect them from a hazardous liquid, their body can no longer evaporate sweat.
In a warm environment, that suit quickly becomes a sauna, inducing rapid, potentially fatal heat stress. You protected them from the chemical, but you introduced a life-threatening thermal hazard.
Even something as simple as heavy leather gloves, required to prevent lacerations, significantly reduces the tactile sensation and manual dexterity of the worker's hands, making it far more difficult to operate fine machinery controls safely.
And a 6-foot shock-absorbing lanyard on a fall arrest harness can easily become a snagging hazard if the worker is moving around rotating equipment.
It is a precarious, constant balancing act. Every piece of PPE requires a secondary risk assessment to ensure the cure isn't worse than the disease.
There is also a significant legal and financial mandate attached to PPE that is explicitly outlined in the ISO 45001 standard.
Right. Because PPE is the last line of defense against hazards, the employer has failed to eliminate or engineer away. The standard notes that in many countries, legal requirements dictate that all necessary PPE must be provided at no cost to the workers.
The employer bears the complete financial burden of maintaining this final vulnerable barrier.
The irony of PPE is profound, especially when you consider public perception. When the general public, or even the media, thinks about workplace safety, the universal symbol that immediately comes to mind is a person wearing a brightly colored hard hat and a high-visibility reflective vest.
It is the visual shorthand for the entire safety profession.
But when you truly understand the ASP exam material, and you internalize the fundamental laws of the hierarchy of controls, you realize that image represents the exact opposite of ideal safety.
A worker in full PPE is a visual confirmation that the company was unable to avoid the hazard, unable to eliminate it, unable to substitute it, and unable to engineer a physical barrier.
The symbol of safety is actually the symbol of relying on the absolute least effective method of protection.
It is a sobering realization for anyone entering the field. Understanding these individual tiers theoretically, avoidance, substitution, engineering, administration, PPE is crucial for passing the test.
It is like knowing the distinct flavor profile of individual ingredients in a recipe.
But a safety professional does not operate in a textbook. Their actual job is standing in the middle of a chaotic industrial facility and blending these concepts together.
That brings us to the operational reality of risk management, and a concept the industry calls prevention through design, or safety through design. This is where the hierarchy of controls is utilized at its maximum potential.
Prevention through design is the strategy of integrating hazard analysis and risk assessment methods incredibly early in the life cycle of a project.
You aren't walking onto a finished factory floor and trying to figure out how to put a guard on a dangerous machine.
Right.
You are applying the hierarchy during the blueprint phase.
You are conducting risk assessments while the facility is merely a CAD drawing on a computer screen, before a single yard of concrete is poured, and before a single piece of machinery is manufactured.
It is the ultimate manifestation of avoidance and elimination. You are literally designing the hazard out of existence before it ever enters the physical world.
If the blueprints show a valve that requires a worker to climb a 20-foot ladder to turn it manually, prevention through design mandates that you alter the blueprint to relocate that valve to ground level.
Or you specify an electronically actuated valve controlled from a safe distance. You eliminate the fall hazard on paper.
But we have to acknowledge that most safety professionals do not spend their careers designing brand new facilities. They inherit legacy systems. They work in existing plants with old equipment.
In the real world, you are rarely going to find a perfect single-step solution on the hierarchy. You cannot just pick engineering control and consider the job done. The exam scenarios will heavily test your ability to utilize a strategy of overlapping controls.
Let's walk through a complex scenario to demonstrate how overlapping controls function in practice.
Okay, let's hear it.
Assume you are the safety manager at a facility, And a new production requirement introduces a process that emits a highly toxic vapor. You perform your risk assessment. Your ultimate top-tier goal is to install a permanent, custom-engineered local exhaust ventilation system to capture the vapor at the source.
That is the engineering control.
However, you consult with the engineering firm and they inform you that it will take 6 months to design the system, fabricate the ductwork, and install the massive exhaust fans.
You cannot halt production for 6 months, but you absolutely cannot allow workers to breathe the toxic vapor during that interim period.
This is exactly where the dynamic application of the hierarchy comes into play. You have your permanent solution identified, but you must drop down the hierarchy to establish interim protection.
While you wait for the engineering control to be built, you implement strict administrative controls. You rewrite the procedures to restrict physical access to the vaporization area, allowing only absolutely essential personnel to enter.
You alter the work schedule so no single worker is in the area for more than 30 minutes.
And because the administrative rules still leave the workers exposed to the vapor when they are in the room, you are forced to drop to the absolute bottom of the hierarchy. You mandate rigorous PPE.
Every essential worker entering that restricted zone must be medically cleared, fit tested, and required to wear a specific chemical cartridge full-face respirator.
You have layered administrative restriction in PPE as a temporary stopgap. Fast forward 6 months, the engineering contractors installed a custom local exhaust ventilation system.
You conduct air monitoring tests and verify that the engineering control is successfully capturing 99.9% of the toxic vapor before it reaches the breathing zone.
Once that engineering control is active and verified, you can fundamentally shift your strategy. You can strip away the arduous requirement for the respirators, moving your primary protection strategy back up the hierarchy to a far more reliable, less burdensome care.
It is a highly fluid, dynamic process. You are constantly evaluating the feasible application criteria, shifting methods, and combining tiers based on what is technologically and operationally possible at that exact moment.
And crucially, the source materials heavily emphasize that throughout this entire process, whether you are designing an enclosure or selecting a respirator, the selection of these controls must actively involve the frontline employees who actually perform the job.
The employee involvement mandate cannot be overstated. If a safety professional isolates themselves in a climate-controlled office and attempts to design an administrative operating procedure, or unilaterally selects a specific brand of cut-resistant gloves without ever consulting the floor worker who has to use them,
there is an extraordinarily high probability that the solution will fail in practice.
if the safety manager selects a glove that is too thick, making it impossible for the worker to feel the tactile feedback needed to press a small calibration button on their machine, the worker is not going to stop production.
They're simply going to take the glove off, perform the task barehanded, and expose themselves to the laceration hazard.
By actively involving the employees in the hazard analysis and the selection of controls, you ensure the proposed solution is actually functional and workable in the reality of the shop floor.
Because the workers understand the micro-realities of the task better than anyone. So when you are sitting in that testing center staring at a complex, paragraph-long scenario question on the ASP exam, you must evaluate the feasibility criteria we have discussed, and you must be prepared to look for the blended solution.
The correct answer is rarely going to be a single action.
The most defensible, accurate answer might be substituting a highly toxic chemical for a milder one and adding an engineered local exhaust ventilation system and requiring administrative training on the new chemical. It requires a holistic systems engineering mindset.
It requires you to think beyond the immediate hazard and view the entire production process as an interconnected ecosystem.
Let's take a moment to briefly recap the core order of precedence to ensure the structure is thoroughly reinforced. We begin at the absolute top, the most proactive and effective tier, avoidance and elimination.
This is altering the business plan to dodge the hazard entirely, or physically removing an existing hazard from the environment. The risk drops to zero because the threat no longer exists.
Immediately following that is substitution. We cannot remove the hazard, so we replace the dangerous chemical, process, or machinery with an alternative that possesses a fundamentally lower potential for severe harm.
When removal and substitution are exhausted, we deploy the physical barriers, engineering controls. We leave the hazard in the environment, but we utilize design changes, acoustic enclosures, ventilation systems, and interlock guards to physically isolate the human being from the kinetic or chemical danger.
When engineering reaches its feasible limits, we cross the boundary into managing human behavior. we implement administrative controls.
We attempt to control the way people work through stringent policies, lockout, tagout procedures, rotational scheduling, and hazard communication training. This tier relies heavily on continuous management enforcement and perfect human compliance.
And finally, when all else fails, or while we wait for better solutions, we deploy the last resort, personal protective equipment.
We armor the worker's body, fully aware that this gear does not remove the hazard, requires intense maintenance, is subject to failures, and may introduce new hazards into the workplace.
The foundational rule you must carry into the exam is this: moving up the hierarchy increases your objective effectiveness and protection, while moving down the hierarchy drastically increases your reliance on the unpredictable variable of human behavior.
Internalizing that philosophical framework is the key to mastering Domain 2.
Now, before we conclude this discussion of the source material, I want to leave you with a forward-looking thought experiment, specifically based on a minor but crucial note in the Domain 2 exam blueprints.
Oh, the emerging text section.
Right. The blueprints explicitly state that a modern safety professional must maintain an awareness of emerging technologies. They are referencing the rapid integration of data mining, advanced robotics, drone deployment, and artificial intelligence into the industrial sector.
The operational landscape is shifting at an unprecedented rate, and our traditional frameworks are going to be tested by these advancements.
So, ponder this scenario as you continue your studies. Imagine a petrochemical company needs to perform a structural integrity inspection inside a highly toxic, confined space reactor vessel.
Historically, this required an intense combination of administrative permitting, engineered ventilation, and heavy PPE to send a human inside.
But today, the company decides to purchase an AI-piloted advanced sensor drone. They fly the drone into the reactor to perform the entire inspection, completely removing the human worker from the equation. Where exactly does that technological intervention fit on the classic hierarchy?
That's a great question.
Is deploying a drone an engineering control because you have utilized an advanced machine to isolate the human from the toxic environment? Or is it elimination because the human being has been completely and permanently removed from the physical process entirely?
It is a profound question because it actively challenges the rigid boundaries of our traditional definitions. As AI and robotics evolve to take over the most inherently dangerous tasks in our physical world, it forces us to ask, will the classic hierarchy of controls require an entirely new tier?
Will automation eventually sit at the very top, reigning even above elimination?
It is a fascinating dilemma, and it is exactly the type of complex, systems-level problem you might find yourself answering in your future career as a certified safety professional.
Keep that roof leak analogy firmly in mind. Always focus your efforts on designing out the hazards first and rigorously evaluate the human element. Good luck on your exam prep, and we'll see you on the next edition of QHSE Talks.